Right now, as you read this, the International Space Station is bleeding air into the vacuum of space at an alarming rate, and the people responsible for fixing it can't even agree on whether the problem exists. This isn't a minor technical glitch or routine maintenance issue. This is a fundamental structural failure that NASA has quietly classified as their highest-level threat, a designation reserved for scenarios that could kill the crew or destroy humanity's most expensive construction project. The $150 billion orbiting laboratory that represents the pinnacle of international cooperation is quite literally coming apart at the seams. And the agencies managing it are engaged in a dangerous game of denial and deflection that puts lives at risk with every passing orbit. Here's what makes this situation truly disturbing. NASA has acknowledged internally that the station faces both maximum probability of failure and maximum consequences if that failure occurs, their dreaded 5/5 risk rating. Yet publicly, they're maintaining an everything-is-fine narrative that contradicts their own data. Meanwhile, their Russian partners, who control the segment where the problem originates, insist they've completely solved an issue that NASA's own atmospheric readings prove is getting worse. This isn't just bureaucratic disagreement. It's a fundamental breakdown in the transparency we've been promised about operations aboard humanity's orbital outpost. When the agencies can't even agree on whether air is escaping, how can we trust them with astronauts' lives? The crisis centers on a component most people have never heard of: the PRK transfer tunnel, a narrow passageway in the Russian segment that connects the Zvezda service module to visiting Progress cargo ships. Since 2019, this tunnel has been developing microscopic cracks that have grown from hairline fractures to gaps that leak atmosphere at an accelerating rate. Think of it as a pressurized aluminum can developing pinhole leaks, except this can is orbiting 408 kilometers above Earth at 27,600 kilometers per hour, and 7 human beings are living inside it. The cracks started small, almost insignificant, losing less than a pound of precious air per day. By February 2024, that rate had more than doubled to 2.4 pounds daily. By April, it had spiked to 3.7 pounds, nearly quadrupling in just 2 months. At this rate of acceleration, the station is hemorrhaging its life-sustaining atmosphere faster than they can replenish it. The situation has become so critical that NASA was forced to delay the highly publicized Axiom 4 mission, a commercial spaceflight carrying paying customers to the ISS that was scheduled for June 12, 2024. Imagine spending $55 million for a ticket to space only to be told your flight is postponed indefinitely because the destination might catastrophically decompress. The official NASA statement claimed they needed time to work with Roscosmos to understand the most recent repair efforts, but sources within the agency paint a darker picture. They delayed the launch because they genuinely don't know if it's safe to dock additional spacecraft to a station that might suffer explosive decompression. Every additional vehicle that connects to the Russian segment adds stress to already failing metal, potentially accelerating the timeline to disaster. In a remarkable display of either incompetence or deliberate deception, the Russian space agency Roscosmos declared in June 2025 that the air leak had been 100% sealed following their latest repair efforts. They presented data showing stable pressure within the PRK module as proof of their success. NASA, desperate for good news, initially endorsed this claim. But here's where the story takes a sinister turn. Independent measurements from multiple sources within NASA show that the overall station pressure continues to drop at an alarming rate. The air has to be going somewhere, and if the PRK module is truly sealed as the Russians claim, then where? This isn't a small discrepancy that could be explained by measurement error. This is a fundamental contradiction that suggests someone is lying about the state of humanity's most important off-world asset. According to Eric Berger at Ars Technica, who has cultivated a network of NASA insiders over decades of space journalism, the most likely explanation is both ingenious and terrifying. The Russians didn't actually fix the leaks in the PRK module. They simply closed the hatch between it and the Zvezda module. Then that hatch itself began leaking. This created the illusion of stable pressure in the PRK because air from the main station was now feeding through the faulty door seals into the damaged tunnel, maintaining equilibrium while the entire system continued losing atmosphere to space. It's like claiming you've fixed a leaking pipe by opening a second leak that happens to flow into the first one. The pressure stabilizes, but you're still losing water, now from two places instead of one. If this theory is correct, the Russians have not only failed to fix the original problem, but have actually created a second failure point while claiming complete success. To understand why this is so dangerous, you need to understand what the PRK module actually does. It's not just a passive tunnel. It's a critical component that experiences extreme stress during every docking operation. When a 7,000-kilogram Progress spacecraft approaches at several meters per second and latches onto the station, the impact forces travel through the PRK's aluminum structure like a bell being struck. These forces have been accumulating for over 2 decades, each docking adding microscopic damage to the metal's crystalline structure. The module also experiences thermal cycling, swinging from 150th degree in Earth's shadow to plus 121 degrees in direct sunlight every 90 minutes. That's a temperature swing of 278 degrees Celsius 16 times per day for 24 years. The metal expands and contracts with each cycle, creating stress concentrations at every joint, rivet, and weld. The cracks in the PRK didn't appear overnight. They're the culmination of a quarter-century of accumulated damage that everyone saw coming, but no one wanted to acknowledge. NASA and Roscosmos have known since at least 2019 that the module was developing structural problems. Initial inspections found hairline cracks so small they could only be detected with specialized equipment. Cosmonauts attempted repairs using a space-age version of caulk, essentially applying sealant to the cracks like you'd fix a leaking window frame. These repairs would hold for weeks or months before failing, requiring constant reapplication. By 2021, the cracks had grown large enough to be photographed, spreading like spider webs through the tunnel's interior walls. By 2023, the leaks had become audible. Cosmonauts reported hearing a faint whistle when near the module, the sound of their atmosphere escaping into the void. The acceleration of the leak rate tells a terrifying story of exponential degradation. From 2019 to early 2024, the station was losing less than 1 pound of air per day, concerning but manageable with regular resupply missions. Then, something changed. Between February and April 2024, the leak rate didn't just increase, it multiplied. Going from 0.9 pounds to 3.7 pounds per day in just 8 weeks suggests the cracks aren't growing linearly, but are approaching a critical failure threshold. Materials scientists call this crack propagation acceleration. When microscopic fractures reach a certain size, they begin growing exponentially faster under the same stress. It's the same phenomenon that causes a small chip in your windshield to suddenly spiderweb across the entire surface. The difference is that when your windshield fails, you pull over. When the ISS pressure hull fails, people die in approximately 15 seconds. NASA's internal risk assessment system uses a 5x5 matrix that every engineer knows by heart. The horizontal axis represents probability of occurrence, from highly unlikely, 1, to near certain, 5. The vertical axis represents consequence severity, from negligible, 1, to catastrophic, 5. Most ISS systems operate in the green zones, low probability, low consequence. A few critical systems hover in the yellow, moderate risk that requires monitoring. The PRK module leak has been classified as 5555, maximum probability, maximum consequence. This is the classification reserved for scenarios like complete loss of station or loss of crew. To put this in perspective, only 3 other times in ISS history has a threat reached 555 status. The 2007 computer failure that nearly caused abandonment, the 2013 ammonia leak that required emergency spacewalks, and the 2021 Naka thruster incident that sent the station into an uncontrolled spin. The most terrifying aspect of this crisis is the suspected root cause, high cycle fatigue, a phenomenon that's killed more people in aviation and space than any other structural failure mode. Here's how it works. Every material has a fatigue limit, the number of stress cycles it can endure before developing cracks. For the aluminum alloys used in the ISS, that limit is typically around 10 million cycles for the stress levels they experience. The PRK module has now endured over 140,000 thermal cycles, millions of pressure variations from docking operations, and countless vibrations from reboost maneuvers. Each cycle causes microscopic damage to the metal's crystalline structure. Atoms shift positions, creating voids and dislocations that accumulate over time. Eventually, these microscopic defects connect, forming cracks that propagate through the material. The insidious nature of high cycle fatigue is that it provides no warning. The metal maintains full strength until the instant it fails catastrophically. To understand high cycle fatigue viscerally, try this experiment. Take a metal coat hanger and bend it back and forth. The first bend is easy. The metal is ductile and compliant. The second bend requires slightly more force as the metal begins to work harden. By the 10th bend, you'll notice the metal becoming stiff and brittle at the bend point. Somewhere between the 15th and 20th bend, the hanger will suddenly snap with no warning. That's high cycle fatigue in action. Now imagine that coat hanger is the aluminum pressure hull of the ISS, and instead of bending it with your hands, it's being flexed by temperature swings, pressure changes, and mechanical loads 16 times per day for 24 years. The station's hull has been work hardening for decades, becoming increasingly brittle with each passing orbit. We're somewhere between bend 15 and bend 20, and no one knows which flex will be the final one. Here's a fact NASA doesn't advertise. The International Space Station is operating 5 years beyond its original design life. When construction began in 1998, engineers designed the station to operate safely until 2020, with possible extension to 2024 if everything went perfectly. We're now in 2025, pushing toward a proposed extension to 2031. That's like driving a car designed to last 200,000 miles for 350,000 miles and wondering why parts are falling off. The station was never intended to endure this many thermal cycles, this much radiation exposure, this many docking operations. Every day it continues operating is a day beyond its safety margin, a gamble that the accumulated fatigue damage hasn't reached critical levels. The Zvezda module, where the leaks originate, is even older. It was constructed in the 1980s as a backup for the Soviet Mir station. This critical component is nearly 40 years old, built in a different era with different standards and different expectations. History offers a chilling preview of the ISS's potential fate through its predecessor, the Soviet-Russian Mir space station. Mir was designed for 5 years of operation, but was kept flying for 15 years through a combination of political will and duct tape engineering. By its final years, Mir had become a death trap, constant air leaks requiring daily repairs, failing life support systems held together with improvised fixes, and a collision with a Progress spacecraft that nearly killed the crew. The station's final years were marked by cascading failures. Fixing one problem would cause another, like a cosmic game of whack-a-mole. Cosmonauts spent more time repairing the station than conducting science. Eventually, even the Russians admitted defeat, deorbiting Mir in 2001 before it could fail catastrophically. The ISS is following the same trajectory. Designed for 15 years, pushed to 30, accumulating failures faster than they can be repaired. This structural crisis is unfolding against a backdrop of institutional failure at NASA. The agency currently lacks a permanent administrator, operating under acting leadership during one of the most critical periods in spaceflight history. Budget constraints have forced the cancellation of multiple ISS upgrade programs that could have addressed these issues years ago. The station's annual operating budget has been slashed from $4 billion to $3 billion, forcing managers to choose between essential repairs and keeping the lights on. Meanwhile, Congress demands the station continue operating until at least 2031 to justify the commercial space stations being developed as replacements. It's a catch-22. The station must keep flying to maintain America's space presence, but keeping it flying increases the risk of a catastrophic failure that could set back human spaceflight for decades. The geopolitical dimension adds another layer of danger to an already critical situation. The ISS represents one of the last remaining venues for U.S.-Russia cooperation, a partnership both nations are reluctant to abandon despite their terrestrial conflicts. This political necessity creates perverse incentives. Both sides minimize problems to avoid giving ammunition to those who would end the partnership. Russian officials, facing sanctions and budget constraints, have every reason to downplay issues in their segments. They can't afford major repairs and can't admit they can't afford them. American officials, desperate to maintain the station until commercial replacements are ready, accept Russian assurances they know are false. The result is a dangerous conspiracy of optimism where both parties pretend problems don't exist, because acknowledging them would force decisions neither wants to make. Lost in the technical discussions and political maneuvering are the 7 human beings currently living aboard this deteriorating station. These astronauts and cosmonauts wake up each day knowing they're inhabiting a structure that could suffer catastrophic decompression at any moment. They can hear the whistle of escaping air. They can see the makeshift repairs, the sealant and tape covering cracks like Band-Aids on a hemorrhaging wound. They train constantly for emergency evacuation, knowing they might have seconds to reach their spacecraft if a breach occurs. Yet they continue their mission, conducting experiments, maintaining the station, and projecting confidence during public communications. Their bravery is remarkable, but should we be asking them to risk their lives aboard a station that both NASA and Roscosmos internally acknowledge has reached maximum risk levels? The station's degradation threatens to undermine the entire commercial space economy just as it's beginning to flourish. Companies like Axiom Space, which has invested hundreds of millions in developing commercial modules and space tourism, depend on the ISS as their initial destination. SpaceX and Boeing have spent billions developing crew vehicles specifically to service the station. Dozens of companies conducting microgravity research have experiments scheduled years in advance. If the ISS fails catastrophically, either through explosive decompression or a forced emergency abandonment, it could trigger a cascade of bankruptcies and lawsuits that sets back commercial space development by decades. Investors would flee the sector, viewing space as too risky for commercial ventures. The promise of a thriving space economy would evaporate along with the station's atmosphere. The most damning evidence of deception comes from the data itself. NASA maintains multiple independent systems for monitoring station atmosphere, pressure sensors in every module, gas analyzers that track composition, and ultrasonic leak detectors that can pinpoint breaches. These systems all show consistent atmospheric loss that can't be explained by normal operations. Yet when confronted with this data, Russian officials point to their single pressure sensor in the PRK module showing stable readings. It's like claiming your house isn't on fire because the thermometer in one room shows normal temperature while smoke pours from every window. The discrepancy is so glaring that it suggests either massive incompetence or deliberate falsification of data. Neither explanation inspires confidence in the station's continued operation. Engineers have proposed multiple solutions to the crisis, all of which have been rejected for political or financial reasons. The most obvious: seal off the entire Russian segment and rely solely on American life support systems. Technically feasible but politically impossible, it would effectively end the international partnership. Another option: send up a repair mission with advanced welding equipment to properly fix the cracks. Cost estimate: $500 million and 6 months of preparation that NASA says it can't afford. A third proposal: accelerate deployment of new modules to replace the failing Russian segment. Timeline: 3 to 5 years, assuming funding that doesn't exist. Every solution requires admitting the problem's severity, something neither NASA nor Roscosmos seems willing to do publicly. Materials scientists who study fatigue failure describe a phenomenon called critical crack length, the point at which a crack becomes unstable and propagates catastrophically. For the aluminum alloys used in the ISS, this length is typically 50 to 75 millimeters under the station's operating pressure. Once a crack reaches this length, it can grow from hairline to complete structural failure in milliseconds, far faster than any human or automatic system could respond. We don't know the exact length of the cracks in the PRK module because many are in inaccessible areas behind panels and equipment. We're essentially flying blind, hoping we haven't already passed the critical threshold. It's like playing Russian roulette, where we don't know how many chambers contain bullets or how many times the trigger has been pulled.